Okay, so I'm going to attempt to cover practice problem number 9 and number 10 that we covered in class, just to give you a review if you need it and in case you missed it. So practice problem number 9 kind of picks up where the last video left off, and we were talking about titrations of weak acids. Now, when we're titrating a strong acid and a strong base, we get a curve, and I'm going to switch back here, that's a little bit different. It starts much lower and it's much steeper and it kind of curves like that. All of our titration curves are going to be this S curve here. Okay. Practice problem number 9 specifically asks us three things. We start with hydrocyanic acid with a Ka of 6.2 times 10 to the negative 10th, and we dissolve it in water, and we get a 50 milliliter sample of a 0.1 molar solution. And we're going to titrate it with NaOH. And it asks us to calculate the pH in three different solutions. One after we've added 8 milliliters of NaOH, one at the half point, and the other one at the equivalence point. So obviously to solve this, the first thing you need to do is be able you need to know what halfway point and equivalence point is. So if we go back here to this video, or to this previous slide, we can look at the titration curve. The equivalence point is going to be found right here in the middle of the vertical line of a titration curve. And it is, well, equivalence point means equal. So what we're doing is we've added the same amount of base as the acid that we started with. So we have equivalent moles. So at that point, it's the equivalence point there. Okay. If it's a strong acid and a strong base that we're titrating, that equivalence point will be pH of 7. You don't even have to do calculations for it because it's neutral. But if it's a weak acid that we're titrating, then as you can see here in this example, the equivalence point is a bit higher. And the weaker the acid, actually, the higher that will get. Okay. The other thing is the halfway point. And the halfway point is halfway between the beginning and the equivalence point. So we tend to find it right here in the middle of this buffer zone. And I call it a buffer zone because if you look in either direction, the pH isn't really changing very much. So this is our buffer zone. So at the halfway point, we've added half as many moles of base as the acid that we started with. All right, so let's go back to this problem, and I'm going to try and work this on another document as we kind of go along. Okay, so I would highly recommend, I hope you already have it out, but if you don't, get out practice problem number 9, and I'm going to do my best to kind of work it in the background here. Okay. So we have hydrocyanic acid, and we have 50 milliliters of it right here, and it's a 0.1 molar sample. And we're going to titrate it with 0.1 molar NaOH. Calculate the pH. After 8 milliliters of 0.1, NaOH has been added. Well, the first thing is we need a reaction. So if we started with HCN, okay, and we're adding OH, and only OH because we don't really, hopefully, you know at this point that the sodium doesn't matter, so we're going to just leave that out. But when we mix these two together, we're going to get a reaction, and the first thing that's going to form is water, okay? And the other thing we're going to get is cyanide, and that is our conjugate base. Okay, so we're going to set up a before and after table because there is a reaction. And so the main components here is HCN, OH, water. We don't worry about water because water is a liquid and it's not a part of our equilibrium, and our cyanide, our conjugate base. Okay, so before anything happens, we have some hydrocyanic acid. We have 50 milliliters of it at a 0.1 molar solution. So remember, our before and after table is done in moles because it's stoichiometry. And I'm going to use millimoles like the previous video. Okay, so we have 5 millimoles of acid. Okay, and we're adding 8 milliliters right here, 8 milliliters of 0.1 NaOH. And if we multiply that out, we get 0.8 millimoles of that. And of course, we don't have any cyanide just yet. All right, so if we look at these two, and they're reacting in a one-to-one relationship here, okay? OH is definitely limiting, so we're going to put a 0 there. but we're going to lose 0.8 of the hydrocyanic acid during this process. So now I'm going to have 4.2 millimoles left. Okay, and then the cyanide, I'm going to make 0.8 millimoles. All right, so these are the two values that we are going to put into the Henderson-Hasselbalch equation. So if you remember that, that is pH equals pKa plus the log of the base over the acid. Okay, so we need to solve this, we need to figure out what our pKa is, and our pKa is figured out from our Ka up here, 6.2 times 10 to the negative 10th. And if you remember, P just means negative log. So we're going to take the negative log of this guy. And when I do that, I get 9.207. Actually, I'm going to round that up to 8. Plus the log of the base, which is 0.8 millimoles. So we're going to put 0.8 there. Divided by the acid, which is 4.2. Okay, so if you put that in your calculator, you should be getting something right around 8.49. We have, let's see here, 3 sig figs here, 3 here, 3 here, but our Ka is only 2, so we're going to leave it with 2 sig figs, which means 2 decimal points. All right, so that's A. Okay. So the next one is at the halfway point. So I tell you what, I'm going to erase some of these, okay, because I'm going to leave the rest of the setup the same. All right, so we're starting with our 5 millimoles of acid. And as I said, for a halfway point, what it means is I'm adding half as much base as I have acid to start with, which means I have 2.5 millimoles of hydroxide that I'm adding. I don't have any conjugate base. Okay, OH is still limiting, so afterward I'm not going to have any of that left. 5 millimoles of the acid. Again, this is reacting at a 1-to-1 relationship. So I'm going to have 2.5 millimoles of the acid left. And over here, if this is limiting, my 2.5 millimoles is now going to be my conjugate base too. So here's the halfway point. And if you look, we have this unique situation. Because I've added half as much base, I have the same amount of acid as I have base, okay? Of the conjugate base, rather. So if you remember what we were talking about in class the other day, if B over A is 1, if my acid equals my conjugate base at equilibrium here, this is going to be the log of 1, which hopefully you know is 0. So actually, anytime you have the halfway point, the pKa is going to be equal to the pH, okay? Because the log of 1 is 0. So in this case, when we already saw for our pKa in part A, our pKa is 9.21. Okay, so part B is done. All right, so let's take a look at part C. Okay, again, I'm going to erase some of these, and because we're going to use the same setup, it's the same reaction. So part C wants to know the pH at the equivalence point. Okay. Equivalence means equal. So equivalence point means I'm going to add as much hydroxide as I have hydrocyanic acid. So I'm going to add 5 millimoles of base. Okay, don't have any conjugate base yet. And we don't have anything that's limiting. These are going to react to completion. Okay, but it's going to leave me with 5 millimoles of cyanide. Okay, again, these two are going to react to completion. Okay, and this is going to produce 5 millimoles of this. So here's the thing. At the end of this reaction, I only have a base. I can no longer use this Henderson-Hasselbalch equation. That's not going to do me any good anymore. So I'm going to just kind of cross him out. If I don't have a base and an acid to plug into this equation, I can't use it. So we have to kind of concentrate on what we do have. So at the equivalence point, the only thing I have is the conjugate base. It's a weak base. So we're going to solve it just like we did the weak bases in our previous unit. we're going to have x squared over the concentration minus x. Now, that's the trick, isn't it? Because we have to find out what the concentration is. Just because we know the moles, please don't forget, you cannot put moles in this equation, right? So the Kb, that's another thing too, isn't it? We have to find the Kb. They gave us the Ka of its partner, but did not give me the Kb. So let's start with that one. To find the Kb, we take Kw divided by Ka to get the Kb. All right, so that's our first calculation real quick. Sorry, and I'm going to do this. I forgot to do this one, so I'm going to do it real quick. All right, and I get 1.61 times 10 to the negative fifth. All right, and we're going to set this equal to x squared over original concentration minus x. So this is going to be another side calculation. I have 5 millimoles, but I have to get concentration, I have to put it over the total volume. So we got to go back up here and take a look. I know I started with 50 milliliters of acid. It told me that. Okay, so I know I have 50 milliliters of acid. Okay, but I have to figure out how much base I added at the equivalence point. Well, this one's a little bit easier because the concentration of the base is the same as the acid. So therefore, the volume must be the same if the moles are the same. So I'm going to add 50 milliliters here. So basically, I'm taking my 5 millimoles divided by my 100 milliliters here, and I get a 0.05 molar solution. So back up here to my Kb, I'm going to put 0.05 molar minus x. Okay, and I'm going to solve for x. My Kb is pretty small, so I think we're going to be okay getting rid of that. So if you could, plug that into your calculators. Again, we've got the 1.61 times 10 to the negative fifth times your original concentration of 0.05. Don't forget to square root. And I get an x of 8.98 times 10 to the negative fourth. Okay, but you have to remember what this equals. This is Kb, and this was a base. So x is actually equal to the hydroxide concentration. So when you take the negative log of this, you're going to actually get POH. Okay, so take the negative log of your x, and you're going to get, remember this is POH, and I got 3.047, right? But we need pH. Again, hopefully you remember this as well. That means 14 minus POH will give us pH. So our pH in this one, then for the third one, we should have 8.49 for A, 9.21 for B, and 10.96 for part C. So to wrap this up, we're going to do one more practice problem, but I want to just summarize a couple of things that we see in some of these titration problems. Okay, it's not necessarily the amount of acid that you have, it's not about the strength of the acid. It's about how much of it you have. Keep in mind the same amount of HCN as you would have, say, HCl is still going to take the same amount of NaOH to neutralize it. It's just that you're going to get a different product when you do that. So when I neutralize HCl with NaOH, my conjugate is sodium chloride, which has no acidic basic properties to speak of. Okay, but when I neutralize HCN, I get a conjugate base, and since HCN is fairly weak, that conjugate base is fairly strong. So it still takes the same amount to neutralize it. It just depends on how much you have. So please remember to do stoichiometry, your mole tables, your before and after tables, whatever you want to call them. Make sure that you're doing those first. The second thing you need to remember is the equivalence point is definitely affected by the strength of the acid. So as the strength of the acid weakens, its equivalence point is actually going to keep getting higher and higher on the scale. So like acetic acid, okay, it's fairly weak, and its equivalence point is 8.72. But hydrocyanic acid is far weaker, and at equivalence point, it's already all the way up there at 11. Okay, so the smaller the acid strength, the stronger the conjugate base, and we see that reflected in the equivalence point. In fact, the book even goes to the point of showing you an illustration of some of these different acids and their titration curves. And you just see as they get weaker and weaker, they just get higher and higher on the scale. All right, for the last problem that I want to cover in this video, this problem is all about trying to figure out what is halfway point. So let's read through this. A chemist has synthesized a monoprotic weak acid and wants to determine its Ka value. In fact, this was originally planned to be the titration that I had you try in the last unit. I wanted you to kind of see if you could figure out the Ka of an acid based on the titration, but we'll get to that. To do so, the chemist dissolves 2 millimoles of the solid acid in 100 milliliters of water and titrates the resulting solution with 0.05 molar NaOH. After 20 milliliters of this NaOH has been added, the pH is 6. What is the Ka value for the acid? All right, so I'm going to switch back. Here's this problem. Okay, this is practice problem 10 on your sheet. Okay, first thing we need to do is figure out how many millimoles of acid that we're starting with. And it says right here we have 2 millimoles. Okay, so this is some unknown acid. So I'm going to just put HA. Okay, and we have 2 millimoles. Okay, and I'm putting OH in here. And so I have to figure out how much OH I've added. It says after 20 milliliters of 0.05. So that's 1 millimole. All right, so I'm going to get a conjugate, but not yet. So I'm not going to have any to start out with. And this is not unlike that previous problem that we did. This is limiting. My hydroxide is limiting. Okay, so I'm not going to have any of that. But I'm going to use half of this. So I'm down to 1, and I'm going to make 1 millimole of the conjugate. This is my halfway point. So what they did is, and remember, our pH equals the pKa plus the log of the base over acid. But as we've said, if the base over acid is equal to 1, and they are, 1 over 1, so this is 1, right? And the log of 1 is 0, so the pH equals the pKa. So they told us right here, at this point, the pH is equal to 6. So that means my pH is equal to the pKa, which is 6. So remember to take this back out because we're looking for the Ka of the acid. Okay, we're going to take 10 to the negative 6 to figure this out. Right? So our Ka is 1.0 times 10 to the negative 6th. Okay? I hope that made sense. Please let me know if it didn't, if you need some more assistance with this. The halfway point and the equivalence point, it can be tricky, especially if you tend to get those mixed up. So let me know if you need some help, okay? All right, I hope this has been helpful, and I'll see you in class.